So if we go through bonding and we try to define it, right, all bonds are formed or created by the exchange or sharing of electrons. And we have three main types of bonds that we talk about. The first type are when electrons are exchanged, which basically means something is going to give away an electron, something else is going to take on an electron. Okay, and this type of bond is always formed between a metal and a non-metal. So something that's on the left-hand side of the periodic table and something that's on the right-hand side of the periodic table come together, exchange their electrons, and form a bond. The second type, which is a type that we're not going to cover in this course, but is worth taking a second and noting, we also do have metallic bonds, and those are bonds that are formed between metals, so two things that are on the left-hand side of the periodic table. Now, the last type of bonding, which is the covalent bonds, this is when electrons are shared, and specifically when they are shared between two atoms that fall on the right-hand side of the periodic table, or the nonmetals. So if we look at an example of an ionic bond, so what I've picked here is potassium, which you can find on the left-hand side of the periodic table, and chlorine, which you can find on the right-hand side of the periodic table. Okay, if we go through and we count up valence electrons according to the rules that we talked about on Wednesday in class, right, we note that potassium has 1 valence electron and chlorine has 7 valence electrons. And so if we think about this, right, potassium is going to want to give away 1 electron, and chlorine really wants to accept that electron because everything wants to get to where it either has 0 or 8 electrons around it. So what happens is that potassium gives its 1 electron to chlorine, so both of them ionize, so you end up with K plus and Cl minus, which is also another way of saying you have the formula or you have the compound KCl, or potassium chloride. Looking at another example of this, if we have, or take for instance, say magnesium and bromine, and we look at their valence electrons. So magnesium has 2 electrons in its valence shell, and those 2 electrons are electrons it's going to want to give. And bromine only has a spot for 1 electron. So what ends up happening is we pull in another bromine atom. So we have a place for both of those magnesium electrons to give, or to go. And what we end up with is Mg2 plus, because it gave away 2 electrons, and we have 2 Br minus atoms, or ions. And the reason why they are minus is because each one of them has taken on an electron, and that's how we get MgBr2. And if you think about the way that we talked about in class on Wednesday, where you take the charges and you balance them, right? If magnesium has a 2 plus charge and Br has a minus charge, then it would make sense that when they come together to form a compound, they come together in a ratio of 1 to 2, or MgBr2. Now, when we carry on through our discussion, right, so first of all, right, we went through and we said we're going to talk about ionic and we're going to talk about covalent bonds. Now, covalent bonds, that is when 2 non-metallic elements react by sharing rather than gaining or losing. So now what's going to happen is you're going to have 2 atoms that are actually going to share electrons so they can both have that 8 electron shell. Now, specifically what we also have to note is it's between non-metallic elements. So it will always be elements that we find on the right-hand side of the periodic table. And when this happens and we share electrons, depending upon how many electron pairs we share, right, we form single, double, or triple bonds. So if we look at the example down at the bottom, right, where we have Cl2, so we have 2 chlorine atoms coming together to form a bond. What we know about chlorine based upon the valence electrons, or how it ionizes, right, we know that each chlorine has 7 valence electrons, so it has room to gain 1 electron. It doesn't really want to give up 7 electrons. So if you have 2 of those atoms coming together, the problem comes into the fact that neither one of them wants to give up an electron to make the other electron, or make the other atom happy. So what they do instead is they share those 2 electrons so it can form a bond, and each one of them will have the 8 of electrons. So basically what happens is each of those chlorine atoms get to claim both of those red electrons that you're seeing in that image. If we look at another example, so CO2, for instance, we have a carbon atom that has 4 valence electrons. And so what that's telling us is it either wants to gain or lose 4 electrons. And then we have 2 oxygen atoms, both of which want to gain 2 electrons, so each of them can have their 8. So what ends up happening then, as we put carbon in the center, and carbon is then sharing 4 electrons with each of those oxygen atoms. So carbon puts in all 4 of its electrons to the sharing pool, and each of those oxygen put in 2 electrons to the sharing pool. And as a result, you're getting a total share of 8 electrons, 4 electrons between each set of atoms. And so what you would actually have is carbon double bonded to each of those oxygen because it's sharing 4 electrons or 2 electron pairs total. Now this is not something, so what you see here are Lewis structures, right? And I'm only really providing these Lewis structures to kind of help you guys keep in mind how all of these electrons are either being shared or how they're being either lost or gained in order to form all of these bonds. So now what we get to do is start naming this stuff. Okay, and it's really useful to kind of start with ionic naming because that's the one that seems the most inherently obvious. And the reason why we start with that is because ionic bonds, if you think back to what we had discussed before, right? Ionic bonds will always have an ion that has a positive charge and an ion that has a negative charge. And if you think back to the beginning of our chapter 2 discussion, the thing that's carrying the positive charge is what we call the cation. And so what we do is we start our discussion by how do we name ions? And so if you look here, right, at the first examples that are shown on the page, right, we have the Na plus ion and we have the Mg2 plus ion. Now with cations, or the things that are carrying the positive charge, all we do is just take the name right off the periodic table and we add the word ion to it. So Na plus is a sodium ion, Mg2 plus is a magnesium ion. Okay, now sometimes we have those metals or those cations that fall in that center block, which are the ones that kind of have funny names. And so typically what we do with transition metals, or the things that are in that D block, is we note the ion charge by including Roman numerals. So if we were talking about the Fe2 plus ion, we would say iron Roman numeral 2 in order to name it or let them know by the name that we're talking about the iron that carries the positive 2 charge. You will also sometimes see the iron 2 ion be referred to as the ferrous ion, but more common than not, you'll see it in the Roman numerals. Now, the same can be said with iron 3, right? So it tells us it has a +3 charge. So when we name it, we would say iron Roman numeral 3. You will also sometimes see this named as ferric, but not necessarily always. You see that Roman numeral notation a lot more. And if you look at the next 2 examples, so copper, right? Copper 2, you would note that you're talking about copper 2 by using the Roman numerals, or you could use the name cupric. And if we were talking about that copper 1 ion, it would just be copper 1 in Roman numerals or cuprous. So anytime we're talking about something that we're naming and it's in that center block of the periodic table, we always want to make sure after we name the ion, we're including in the Roman numeral, we're including in parentheses next to it, the Roman numeral of what the charge is. Okay, and so that takes care of how we name cations. So generally speaking, right, if it's any of the ones that are not in that transition metal block, right, we just take the name right off the periodic table, throw the word ion onto the end of it. If it's something that falls in that center block, we name it as is and then include Roman numeral after it with the charge of what we're talking about. Now, to move on to the counterpart, because all of your ionic bonds will have positives and negatives. They will always have a positively charged ion and a negatively charged ion. Okay, when we're talking about the anions, All we're going to do is take the name off the periodic table, and we're going to take the parent part of it, so the root name in it. Okay, you're going to take off that ending part, and you're going to add the suffix IDE. So if we look at chlorine, we would take the parent name chlor, take off the end, and just stick "ide" onto the end of it. So it would become the chloride ion. If you look at oxygen, what we would do is keep the root name or the parent name, so ox, take off the end and add "ide" to it. So it would become the oxide ion. Okay, and that's kind of how it goes if you're trying to name just individual ions. When you are going through and you're naming actual ionic compounds, all you do is name the ions, but you take off the ion ending. So at this point, if you were to take that sodium ion and bond it with that chloride ion, you would be making sodium chloride. So we've taken exactly how we've named the ions, chopped off that ion ending, and just named it as is. On another example, if we were to take MgO, okay, what we would do is just take the two ions. I apologize, that says chloride. It should say oxide. Okay, and you just name it as you would name the ions, but you take off that ION or ion ending. So it would be magnesium oxide. Now notice there's not any prefixes or anything like that. It's just naming the pieces directly off the periodic table. Okay, and we'll notice it's a little bit different when we start talking about covalent bonding. Okay, now coming along or talking a little bit more about this, sometimes when we're talking about ionic bonds, the ionic bond involves using what we call a polyatomic ion. And some of you guys may be familiar with this, some of you may not, but polyatomic ions are groups of covalently bonded atoms that carry a charge. Okay, and what I've done here is I've listed the charge of the ion, the name of the ion, and also the chemical formula. Okay, and you guys would be responsible for knowing the things that are on this table, right? And you would be responsible for knowing all three columns. So you can't forget any of these columns. Okay, and what you will notice is, so for instance, this +1, it applies to both of these. This -1 applies to all of these. And the -2 applies to all of those below it as well. Okay, so make sure you guys are going through, right, and you're becoming familiar with this list. If you want to make flashcards, I know there's also like an iPad and a Droid app out there that you can review and things like that. Definitely some good practice there because you guys are responsible for being able to recognize what a polyatomic ion is. So if we're going to try to name compounds, right, or provide formulas for things that involve polyatomic ions, we have to be familiar with them. So if we come down here, right, we know that calcium is Ca, and we know that nitrate from that table is NO3. Okay, we also know that calcium, when it ionizes, it takes on a +2 charge. And from the table on the previous page, we know that the nitrate ion is charged with a negative charge. So if we were to try to provide the formula for what happens when you make the compound calcium nitrate, remember we just cross our charges, right? So what we end up with is Ca parentheses NO3 and then 2 outside of the parentheses. And now keep in mind, right, we have these parentheses here because we need to note that that nitrate ion is a unit that travels together, and that 2 needs to apply to all of the atoms that are in that specific polyatomic ion. Okay, now if we go in the reverse, so we have an actual formula and we're trying to name it, all we do is we name it just like we name our ionic compounds. So you name the positive portion first, and you name the negative portion or the anion second. So if we look down here, we have NH4. NH4 is in parentheses with the subscript 2. And then we have SO4 after it. Well, NH4 is the ammonium ion, and SO4 is the sulfate ion, based upon what we saw on our previous polyatomic ion chart. So what we see here, right, is that we have ammonium sulfate, right? Just take the names as is, the positive name, the negative name, take off the ion, and call it a day. Okay, so that in a nutshell is how we name things that involve ionic bonds. So something that is coming in and has a positive charge, something that's coming in and has a negative charge. All right, switching gears, we go into what happens with our covalent compounds and how we name them. Okay, what you will notice over on the right-hand side is there's a table, right? And the table gives you some prefixes, and most of these prefixes are going to look familiar. And the reason why we're talking about these is because when we go through covalent compounds, now we care about how many of them are actually there. Now we care about those subscripts, okay? And so we want to be familiar with this chart over here. So when we actually go through and we name covalent compounds, what we will do is first name the first element using the prefix. So if you have nitrogen, for instance, and you have two of them, you would just say di and nitrogen. So again, just pulling the name right off the periodic table. With the second name, it's kind of the same as ionic naming. So you're going to pull it off. You're going to pull the name directly off the periodic table. You're going to drop the ending and you're going to add IDE to it, just like you would with your ionic names. But now what you're also going to include is the prefix. So if we look at the two examples down at the bottom, so the first one is SCl2. Okay, there's only one of that first ion, so we won't use a prefix. So what we would do when we name that portion of it is we would just say sulfur. If you look at the second piece, you have two chlorines. So if you use your general naming conventions, you use the root name, take off the ending, add IDE, and then add the prefix, you would get dichloride. So if you were to name this compound, you would have sulfur dichloride. Okay, if we look at the other example that's on the right-hand side, okay, the first atom that's there is phosphorus. So we name just like we would from the periodic table. So we have phosphorus, and then we need to come up here and use the prefix for 4 atoms. So what we end up with is tetraphosphorus. Then if we look at the second piece, we have 3 sulfurs. And if we follow our naming rules, since it's the second ion listed, what we would do is take the root name, take off the ending, and add IDE. So we get sulfide, and then because there are 3 of them, we use that prefix tri, so we have trisulfide for that portion. And if we were going to name the overall compound, we would have tetraphosphorus trisulfide. Okay, so that wraps up the general naming portion of chapter 2. And what we will do when you guys come in class on Friday is basically we're going to practice this. So we're going to practice being able to recognize if something's ionic or covalent, being able to recognize if something's a monatomic ion versus a polyatomic ion, and then also how you would name various things. So there will be lots and lots of practice on Friday. In the meantime, if you want to practice using different resources on Google or an app, that is totally fine. But if this is a little unclear to you or you need more examples, don't worry, we will go through some more stuff in class on Friday. You will have plenty of practice by the time you leave. Okay, as a